All right. Hello, everyone, and welcome to day 4 of Rust Lab. My name is Latara. I'll be the talk manager for today. We have, for you today, we have a 3-hour workshop by Luca Barbato called From C to Rust and Back, the tutorial. So let me bring him live for his introduction, and then we'll start with the workshop. So let's bring Luca live. Hello, Luca.
Hi.
It's nice to have you here. Thank you so much for your contribution.
Oh, you're welcome. Okay, so
I'll go ahead and introduce you, and then we'll get started for everyone. All right?
okay.
Okay. So let's introduce you. So Luca Barbato, he is an active contributor on core Rust projects. He has helped a good number of projects to provide a good C API for their crates. And what about for today's workshop? Well, Rust provides a seamless way to consume and provide a C-compatible API. In this workshop, we'll explore the tools available and the best practices to convert C libraries to Rust and expose back a C API matching the original, and we'll see what are the current limitations and if there are ways to overcome them. Rust and its ecosystem is maturing, and lots of software is now proving that it is possible to have implementations that are faster and safer than their C, C++, and Python counterparts. Lots of valid software still exists in other languages, though, and providing easy ways to use the high-performance Rust crates gets the best of both worlds. So during this workshop, we'll focus on C and what tools and methods are available to build foreign code in Cargo, generate bindings from C headers, automatically convert C code into Rust, generate C headers from a Rust C API, produce C libraries and related helpers like matching PKG config files, and we'll see how some crates use those tools and try them out with simpler and more complex examples. As a bonus, we'll see how generating bindings for C, WASM, JavaScript, and Python differ in ergonomics and in philosophy. So we'll get started with that in just a second. And for all of those of you who are watching right now, just as before, if you have questions to ask during today's workshop, please ask them in the chat that is specifically for Q&A. It's a circle with a question mark around the chat section, just so we can keep things organized. You will see some slides today, and they are published and downloadable from the agenda page of the site. And we'll also put in chat the Drive link on Google Drive so everyone can download them from there and follow along. All right. So is there anything you would like to add before we get started, Luca?
You said pretty much everything. The last part about comparing ergonomics is a bonus track. So if we have time, we're going to do that. If we don't, if you're interested, I'll figure out how to do that later.
Okay, sounds great. Well, let's get started then. Enjoy, everyone.
Okay. Hi, everybody. I managed to not see how to share my screen anymore. So I might need some help. Okay, I managed to find it. So, welcome everybody. This is the tutorial about moving from C to Rust and back. Last year, I presented my contribution of the topic as a tool. And today, we will see how 1 year later, how things are and what we can do. So before we start, there is a bit of tooling that you should install. So we are going to use C2Rust, and it requires a working C-lang and LVM. For the Mac users, you should install LVM from source and use C2Rust on Git. You should have access to this presentation, so you can click the link. The rest of the tools that we are going to use is, well, obviously Rust. So if you don't, please already install it from RustApp, and Cargo C, and just install it from Grace.io. And this is that from the start. Then, who I am, Lothar already told you who I am. So I have experience in fixing mistakes because I'm a Magento developer. So any kind of code that breaks, I end up fixing in a way or another. I contribute since a long time my mistakes, my open source software as part of Speedyland. And lately I started to use Rust a lot, and it is my main language nowadays. So now I'm going to ask you, who are you and why are you here? So I would like to tell me that either in chat, or if I can make you do that in voice, please do. Who wants to start? I see Pietro Lorefice. Why are you here and who are you? Yes, Pietro is shy. Chris Paulin, hi. Can you tell me who are you and why you are here in the chat, or if they can manage to get you on the screen?
Peter.
Hi, Chris. Okay. Okay. Luca Taviano is working on C and C++ on embedded systems. Okay. Green Seaman. Okay. 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 I'm seeing that lots of you are accustomed to C++, and at least some of you have interest in embedded systems. Okay. somebody using C#. Okay, that will be probably fairly different from your habits. Okay, so I'm saying that about half of you have enough experience on RustWorks. Some of you are probably fairly new. And I hope that during this time you manage to start installing the software, since we are going to use it. And so I guess I can start with my little introduction. And we start with C. So for a statement, lots of great software is written in C. People in love with C++ might agree or not, but pretty much all the software that is really ubiquitous and is really basic is still written in C. And why that? Because you can have a C compiler everywhere. So if your software is written in C, you have a good chance that it's going to work in whichever platform you want to port it. Why that? Well, C is old, it's fairly stable, so you don't have ABI problems like you have in other languages, like C++. And pretty much every other language uses that ABI to integrate from each other because it's stable and simple, and probably a bit restricting nowadays. And for a lot of time, C was the best tool for the job. But obviously, nothing is perfect. And C let you make lots of mistakes because nobody prevents you from making them. So we have lots of great software and lots of amazing bugs in the software, mainly because the language works for the purpose, and the purpose is not preventing you from making mistakes, but just write something on a representation of a CPU that doesn't exist anymore. So C is great, and we have lots of software that is pretty good, but can we do better? Well, Rust is new, and Rust is awesome. It fixes the main problem that you have when you're writing software in C and also in C++. So lots of mistakes cannot be made if you're using safe Rust. And notwithstanding this perk, the resulting binary from some code that is equivalent to something written in C is as fast or even better depending on the situation. So sometimes it makes sense to convert some code base to Rust because you get safety and you got speed. Obviously, you are going to lose something that will be portability, at least for the medium term. Rust already allows you to deploy on embedded platform, strange platform such as Wasm, and a normal platform like ARM, x86, Power, and well, MIPS, if you still care about MIPS. So sometimes it doesn't make sense. If your C code base is battle tested, works, you are very sure that people can read it, is quite a lot of effort to convert it to Rust for maybe a minimal part of improvement. And that's true even more if most of your speed is due specific use of SIMD that happens to be more effective in C than in other languages. If most of your speed is because you rewrote all the important routines in assembly, well, then you can port your code to Rust and don't lose pretty much anything. So what we are going to do today. Today I will show you how you can mix and match C and Rust. So the first part is the simplest thing. You have a C library that you want to use from Rust, and I'll show you how to do that. Then you have the second step, that is you have some C routine that you want to use inside your Rust crate, but it's not a library. And the final part is how to build your Rust crate so it looks like a C library. So if you wrote something that is amazing and you want everybody to use it, and everybody is not using Rust, you want to expose a C API. Possibly you would like to expose a language-specific API. So if you want to use it from Python, you would like to not go through the C bindings if you don't need to, but this is still an option. So what we are going to see is what I think that works well. I will show you in the most painful way which are the trade-offs and what is missing. So you should be ready to download the examples tarball, and in there you will find all the exercise and actually the solution of the exercise that we are going to do today. So this is it. And I'm going to split the process of moving from C to Rust in workflows. So the first one, just using a C library. Second one, integrating. Third one, converting the C code. I made it a specific part of the workflow because this is the part in which we have some automation, but it's still 90% human creativity to get it right or to get it effective. And the last part is how to loop back. So you do all this work, you have this wonderful Rust project that is doing exactly the same thing as the C1, and you want that your former users can keep using it. So why not expose the Rust crate as a C library? So those are the 4 steps, and I guess we can start with the first one. As usual, if you have questions, tell them in the chat and I will try to stop. So this is the most common use case. This is something that is done quite often. And the best practice to do that is to split the true concern. Since every time you want to do that, you have 2 problems. One is you want to use the library. The other is you don't want to write C in Rust. So you want to have an emblematic API, and you want to use the library. Let's split the 2 concern. The first one is called assist crate. It is just the low-level bindings. You just convert a C API to a lookalike that is available from Rust. And the other part is, well, use all the goodness of an high-level language to hide at least some of the details, and in some cases to speed up your development. So what it is assist crate? It is something that is simple. So if you want to convert any kind of C library just to be used from Rust, the process is going to take you just a few minutes. It's a crate, so you have to create using Cargo, and then the main part is just writing a proper build.rs with the right directives. Cargo lets you link external libraries inside the crate. And when you want to expose them, the Rust language lets you tell if a type has an in-memory representation that is compatible with C using this decorator. And if you want that a function has the same ABI as C, you just add the external modifier. On top of it, since Rust does mangle the symbols in a way that is sort of similar to the C mangling, you want to add a decorator that is no mangle to tell Rust about that. And that's it. But most of it is simple and boring, and so it has to be automated. And we have two tools that do that for us. One is systemdebs. So the linking problem is solved mainly if your library is providing a PKG config file. And Rust bindgen consume the C header and produce automatically a correct Rust equivalent. If you want to build the library that you want to wrap in this syscrate, you can do that. There are helpers that let you use quite common build systems. And if the library is simple or doesn't have a build system that you like, you can just call directly the C compiler or even the assembler that you like. So this is our directory structure. And as you can see, a syscrate is that kind of simple. You have the build.rs that contains the additional directive to do the actual work, the usual cargo toml, some place in which you put a single header, since Rust bindgen works with a single header. So if your C library has more than one header, you just use that to fix the problem. And a librs that just contain a few things. So our build.rs is simple. It's not that many lines. I managed to fit it all in a single slide. The first line is to find the library. Systemdebs use the normal PKG config settings. This part is just what we need to get from PKG config where the headers are located, and then we build it. And we store the result, that is a Rust 5 somewhere. This is an implementation detail. Don't want much of it, but this is important. In the Rust bindgen documentation is displaying why we do that. The cargo toml is also extremely simple. We have build dependencies, so the dependencies that are going to be used just for build.rs. And then we have a specific key that is telling systemdebs which kind of package we want. This syntax is pretty much straightforward and the same for everything. Other parts. Our header foo is the libfoo that you find in the examples. Is quite tiny and simple library that I put as an example. So in this case, our libfoo has two headers. We just include them. The librs is Well, to replicate just a single line, this include line, but all this boilerplate is used to avoid warnings and just in case the C library explodes something that doesn't fit the Rust coding standard. And this is a macro that is taking our foo_rs and slapping verbatim inside librs. Concat and so on is basically using the out tier that we use above. This is a scratch directory that is not going to be part of our create distribution. And it's just joined with the name that we decide to create. So that's it. Syscreate is just that. Is it simple enough? Anybody has a question about this so far? I take it as a no. So far for the low level. For the high level, just a few things. So the high level create has to map a C API, so bare pointers, everything that doesn't have any kind of hint about thread safety, and bare functions. So what we can do is to make sure, if we care about thread safety, and we should, have some abstraction to wrap the bare pointers. So we have a way to make the language prevent us to make mistakes. We can lump together function calls, so we can have our data structure and associated methods. Something that you should always do, write unit tests. Even better, if there are unit tests available for the C library, you can pour them in the Syscreate, so you have you're fairly sure that the linking step doesn't have any problem, and then you can bring them up to the high level and convert them to the high level, so you can test that just linking the library is fine, and usually it is, besides when it's not, because some C preprocessor is involved. X264 is an example of that. And then you go up and you make sure that your test work is intended. So far, this is it. And now we are going to put that in practice. So first exercise. So I hope that all of you knows how to make a new crate using Cargo.new. You can pick any C library that you like. I provided libfoo because it's simple and has the right amount of mistakes and the right amount of nice behavior. And you have to do pretty much what it did in the previous slides. So add the dependencies on the cargo TOML, write your header. In the build.rs, use the system devs and LineGen, and then you put everything in librs. And if you want, you can write tests here to test that. I put 2 references, one for system devs, because it's simple, but probably you want to know more details about it. And LineGen, it does have a full explanation on what you want to do, with much more details. And I guess I will give you 10 minutes to try on your own to make your own Syscreate. And I'm going to be here in case you have questions. So just in case, there is an example tag XZ that contains all the code, and inside there you will find a libfoo. But as said, any kind of library that you like or you want to try to grab, you are welcome to try to grab. The library is using a Meson build system, so if you have a question about how to build it and how to install it, you are welcome to ask them. Okay. So anybody had problems in getting the C-squared going? So assuming you don't, and everybody managed to get, okay. So let's say when you want to combine the headers, you just include both of them in a single one. And since probably you would be curious to see how the generic code is, this is it. You can find that deep down the target directory, so just rather copy it. And what you can see is that BindGen already writes tests to make sure that the provided struct is correctly aligned and the fields are correct. So if you run cargo test, you already have some tests for ensure that at least the data structures are correct. And as you can see, this use of external C is very similar to the one that you have in C++. And if you look at the C header, you can see the mappings. And also you can see that we are trying to use the C types. So let's say this is for the representation. This is because it's useful. And this is the test to make sure that the fields are in the right order and they work as expected. Those are our few functions. And this is the same thing for foo-b. So okay, well, for this part, you are not going to need LLVM, so you can try to do that while LLVM is installing, assuming that you have already a C compiler. So this is all I can say for the first exercise, and it should be kind of simple. The only pitfalls that you can have are the problem that you want to have a single header and making sure that the pkg config file is correct. Or if you don't have the pkg config file, pass the right include path and link path to cargo. So this is fairly ugly, I guess. So the next exercise is to make it prettier. So let's make the high-level crate. So another crate, you add the sys library. You can decide if you prefer to have it in the same repo, so you make the two library part of the same workspace, or separate. In that case, you have to do more work. And in syslib, all you have to do is to wrap the C data structures, wrap the unsafe functions, and make sure that your wrapper is safe. and write test. So the reference I put here is how to write test, in case you are not accustomed to that. It's very simple. And regarding how to wrap the data structures and well, wrap the function is pretty much calling them, or in the case of the struct, storing them. In the tarball, you have already a solution, so you can look at that if you don't want to try on your own. And for that, it is another 10 or 5 minutes. You tell me when you are done or when you see problems. Did you install the library? Yes, libfoo. Oh, okay. So you have to install the libraries, just getting picked up by pkgconfig, or you can well, do the advanced thing that is pointing pkgconfig to the right place, so it's going to pick it. And if you are just trying to run the example, make sure that the header in data is pointing to the correct headers. But I hope that you all see how simple it is to wrap your library. Basically, all the hard work is made by Bindgen. So just in case, if you want to install it, you can do it. sure that the library is correct, and then this. Make sure that this part is fixed, since that was a mistake. And then you build everything. For that, we are done for the first exercise. So to show you, I decided to put my full.sys directly inside my full crate, and I end up using the workspace to include full.sys. And now you can see the dependency. Okay, so if you see that error, it's telling you that the command pkgconfig is not available. So you have to install pkgconfig. That's a bit unexpected, but refer to your distribution to install pkgconfig. Okay, so if you see the other error, it's telling you that it's not finding foo. And if it's not finding foo, it's because you forgot to install it. So how to install? To enter the directory, manage on build, or the name that you like. In this case, it's going to tell me that the build directory that already exists. Resume is a build system that is similar to CMake. So it prepares the build directive and then is used Ninja to do the actual building work. Oops. All right. That's the other track. Got to match the version of your library. Okay, so no problem.
Okay, everyone, we are going to take a 5-minute break just to stretch our legs. If you want to keep working on the exercise, that's fine as well, but we'll be back in 5 minutes. So see you then. All right, everyone, we are back from our 5-minute break. So let's start the second session of the workshop. Luca, let me turn your camera and microphone on again, and you can get started. There we are. Welcome back.
Thank you.
Yes, good luck.
So let's do a quick recap. So somebody asked, a simple test can be like this. And then how many managed to come up with a high-level API for the wonderful full crate? Oh, okay. So the name structure, just in case you didn't look at it, something like this. This is one of the important parts. Once you wrap, this is the simplest possible way to wrap a pointer. And this is how to use it. So you have to do an unsave the reference, and then you can use it as you want. You have to make sure that you are dropping. So you are going to destroy the actual C struct, or in this case, C pointer. If you don't do that, everything is perfectly safe because leaking is safe, but it's not nice. Same thing here. Another important difference between C and Rust. In C, you have an array of bytes that happen to work as a string. In Rust, the strings are a specific type. So if you want to bridge between one and the other, you go through CString and CSTR that pretty much take care of converting from a string buffer to a null terminated array of bytes. So this part is important, this part is the same. So if you want, we can take another couple of minutes so you can play with example and see how I implemented it. Or if you feel that most of the concepts so far are clear, we can move to the next step. Okay, we're going to take another couple of minutes. Okay, so if there are one more question about this part, I can take this time to answer it. Or we can try to move to the next part. Good. So far it should be sort of simple enough. The next part, some of the pitfalls that we experienced. So our syscrate depends on the system provided library. So if you are on a certain version of Linux and you forgot to register in the linker cache, well, you don't know why, but it doesn't appear when you are running, not when you're building. And you might not be alone. So somebody might not know Mason, so they have problem building the libraries. So the user that just want to use the syscrate and not care about the details, well, we can do something for him. So now this part is to move the C code that currently is built by Mason inside our crate. So we have two options. One is call Mason from builder-s. So we know how to deal with Mason. We put this knowledge inside builder-s. So the user will have to still install Mason and Ninja and pkgconfig and so on and so forth. But beside that, doesn't have to care about exactly how to use Mason. Or the C code, we know how to call the compiler directly, and we're going to do that. So for the first part, if we have a CMake package, CMake is fully supported. If you have an AutoTools package, there is support for AutoTools as well. Otherwise, you can roll your own. Cargo does provide lots of information that can be used and can be also updated. So at the very end of the whole thing, you have this part. As you can see, some of the information that you might need. So you can pass it to the other build system and it knows. This is fairly useful if you want your syscrate to be cross-compatible. So if you want to cross-compile it, and you are building on your own, this part is important. If you are just calling the compiler, the CCRS does that already for you. If you roll your own, you have to take care of this detail. So how does it look calling Mason from BuildRS? This is a bit more work. So what you're seeing here is just this part. Runner is just command wrap to some defaults. So the first part is we are going to build Mason and we are going to install the whole thing somewhere. Then we are going to build it and then we are going to install it. And then what we are going to do is just to set pkg configs to the array point. This part is sort of simple, and this assert is just part of the larger BuildRS that had been made to build David, that is one of the software that is using Mason as build system. And here you can see that there is even more to come, since your sources have to be somewhere. And in this case, it is fetching the sources and then build them. All of it from BuildRS. This is something that is not exactly great. Because then if you want to have something that is reproducible this way, it's wrong. But if the user just doesn't care, just want to get something done, this is the way. So calling another system and getting your private version of it, obviously a static version of it, since otherwise everything gets even more complicated. It's a bit of work, and there are some additional pitfalls, or at least some additional unknowns, and few more details that you have to care about. So what if you want to just build the code without having to deal with all the specific build systems? Well, CCRS does everything for you. If you happen to have assembly code, NASMRS is the other companion that you would like to use. And in this case, it's sort of simpler. So the part about getting the bindings done is always the same. For that, once you have the sources directly in the crate, you can just build it, and this is just the invocation that is the simplest way, mainly because our full library is that kind of simple. So you get the path of the C code and you build it, and that's it. So now our exercise is to either try to go the way that David did and try to use the cargo features so you can swap from one to the other, as you saw also David BuildRS. And this would be the first exercise. If you want to try that. If you want to skip it because it's relatively a bit of work, and personally I would suggest you to avoid it, is also fine. All in all, what you have to do is to, in our case, put the C code somewhere in the crate, and then code Mason as shown there. There isn't much to, well, be creative about. For the others, you can just try to call CCRS and see how it is, pretty much as shown here. So I guess for those exercises, since we are sort of a bit late, I'm going to give you another 5-10 minutes to play with the crates and see if you can manage to get the knack of getting the Spark build. This is sort of nice but optional, or nice but not so nice, depending if you think about distributing your code outside Crates.io and reproducible builds and so on and so forth. In that case, you have to be more careful and do more work. On the other hand, this is sort of useful if you happen to have foreign code, in this case C, but usually you have nice handcraft ASM that you want to keep, and the process is exactly the same. So everybody's fine and there are no problems so far? Or somebody is seeing any kind of problem? So some shortcoming of this approach as seen in the world. So this is the private builder as that is doing quite a bit of things just to build some assembly code. And as you can see, we end up checking a specific version of the assembler, and the building part is different depending on the architecture, obviously. And as you can see, you end up doing some configuration and then some building. And because CCRS doesn't have any awareness of the freshness of your sources, I ended up writing my own tiny bit of logic to figure out if the sources are fresh or not. And if they are not, they are going to be built. This is another little situation that you would like to improve, since Cargo itself is not going to do more work if it could avoid it. But Cargo is completely unaware of all of it. So all the machinery provided by Cargo is not available from here. And this is something that I would like to fix during the next year, probably. Mainly because if you start having a fair amount of code, this is going to take enough time. And this is going to be built quite often, even if the libraries stay the same. And in the big picture, that could be fairly taxing. Meanwhile, Matteo tried to use it directly in the high-level crate. So if you have other questions, I can answer them. Otherwise, I would move to the next part, that it will be a bit more involving. Is everybody fine with this? Does anybody has additional question about this part? Okay, so we're going to move to the next step. So this process is mainly the one that you would like to do once you got annoyed enough by the problem of getting the right C compiler, getting the right assembler, going back and forth if you are cross-compiling to figure out which kind of define to set in C that is mapping the configuration key that is available in Rust, and so on and so forth. So once upon a time, you decide, okay, I want to do without any C because I like Rust better, I like the tooling better, for a number of reasons, or probably because you are now confident that your Rust code is going to be even faster and easier to read than the equivalent C code. So again, I give you two choices. One is incremental. You start from the CCRS crate, well, to the C source crate, and you just move a function of time. Something that you can do with Rust is quite simple. You can write unit tests to do that. And the other is you automate the whole thing. C2Rust is a quite neat piece of code, even if it's really complex, that converts a large amount of C syntax to something that I call quasi-Rust. Why quasi-Rust? Because it's a direct mapping. So you lose on the table most of the niceness of Rust, but in the end, the Rust compiler is the only compiler you have to care about. This way is sort of useful, but it's pretty much just the start of the journey. So the CSI conversion, you keep the C code around Enclosure. It's there. It's not in a separate project. It's not something that you have to keep around, but you are not always sure that you have it around or you have it in sync. It's fairly easy to keep it as it is. We just change the name of the function, and then you have the perfect way to write unit tests. You call one and the other, and you're done. And usually the C code is more readable than the quasi-Rust produced by C2Rust. That is mainly because C2Rust has to work on the post-processed, well, pre-processed code. So all the defines, all the includes, or the macros are already unraveled by the time the code hits C2Rust. So the code could be quite different, quite more verbose, but at the same time, it could tell you more about the code itself. What's the cons? Well, the cons is that until you are done, you have to have the C compiler around. And that could or could not be something that you like. Conversion and then refactor. You start with everything that is pure Rust. Cons. Well, first, C2Rust is very complex and it has big dependencies. So sometimes it's hard to build. Right now, on Mac, you have to go through a number of hoops. And in general, it's not as straightforward to build as for other tools. And as said, you have to pre-process the sources before feeding it. Well, it does that for you. So the resulting code could be quite ugly and quite misleading. So if you have to decide which way to go, it's fairly up to you. So another pros of that is that you could fool yourself in telling that your problem is solved by just having the automated conversion. And sometimes if your need is just to get the C compiler out of your equation, it's true. But you can do much better after. So this is the introduction, and then the exercise. The first one is pretty much do and convert by hand. Try to look at the Rust standard library and see how the math function work. Look at how you go from floating point to int and back, since the full crate has that difficulties. Look at how the printing function works. Well, those are the basics. And then you can try to integrate the code inside the high-level crate. And then you double check that the test pass. This process is going to take a bit of time if you iterate and you don't have just pre-function to care about. And we have a good example that is ABR 128 that was converted exactly this way. So Sebastian did that this way. You see CC here. And then you see that the EBOM library is that kind of simple. So it's a C file. The BSDQ, and that's it. So low dependency, and this is the cBindgen generated interface that Sebastian directly stored. This part is something that it works up to a point, mainly because our interface sometimes can be platform dependent. So if you just save it without looking at what is inside, you will end up with something that does work on a platform but does not work in other platforms. So between generating and storing, you have to figure out what is right for your library. Since this plan is to convert everything, makes sense to, and this library is really using the tiny amount of the C library, this makes sense. And the amount of C code is fair. It's not something that you are going to do in a day, but it's something that is bearable. The API itself is not exactly great, but this is a good example. And since it was that kind of simple, Sebastian went this way. Well, you can look at the history and see how the code evolves. Something that is interesting when you are writing tests to make sure that everything works. You can use quick check to sort of fuzz the input and have a better code coverage. But this is sort of advanced, and I'm not sure that we are going to have all the time to do that. So back to us. This is the first exercise that is simple enough. So we are waiting. I can answer and get you an example. So what are the good practice to replace function by function? Well, you can look at what Sebastian did, but in general, the idea is you have to have the code built in the crate, because otherwise it's way too cumbersome. But you can do that also in the other way. So you can just replace a single function by commenting out or renaming the C original, and you put at the syslib, the syscrate, the Rust implementation of it, and you keep the same signature. And then you look at the tests and see if they are still passing, if there are tests that exercise the function. If they aren't, it would be good to first thread the test and then convert the function. And if you want to do the way Sebastian did, you keep the two functions around. You name one _C and the other _Rust. And then in the implementation, you pick whichever you want. And then you use Quick Check or similar tools to exercise both and make sure that according to the input that they are getting, the output is going to be the same. And it is a fair amount of work, since I expect that it's going to take 5-10 minutes to convert a single function in our tiny library. And once you have 10 functions, 100 functions, the amount of work is sort of linearly scaling, more or less. So this is one way. If you do not want to build your code, then you have to add an additional namespace and do exactly the same thing using the external library. It tends to be fairly the same, but doesn't give you the correct feedback, since if you're removing a function from the code that you're building, you notice immediately if you remove way too much, because then everything is going to stop working. So this is why I prefer to go through the build yourself and make the change in the C code at the same time as the Rust code path. But it's fairly up to you.
All right, you guys, we are actually going to take another 5-minute break. We're about at the 2-hour mark, so another break, and then we'll continue with the exercises. So happy break. All right, everyone. Hope you had a good break. We are going on to the last part of the workshop today. So take it away, Luca. Thank you.
Okay, I'm back. So let's share again something. So example on how to convert. So we have this, and in this case, I just commented out the C implementation, and I wrote down the Rust implementation of the same, and that's it. The sixth grade exposes exactly the same API, but the code inside now is Rust. And it's that kind of simple. For the second exercise, the idea is to try to do the same, but using C to Rust. So I assume that now everybody has C to Rust installed, hopefully. And in the big README, there are instructions on how to convert single files and how to have C to Rust try to generate the whole project by itself. The final part of the exercise is to just clean up the resulting code from the single file conversion and try to integrate it in the high-level crate. It's not different from what we did here. It's just that a tool did that for us. And well, we have to check and make sure that the tests keep passing. If you want an example on how we did that, the SpixDSPRS or sampler was converted this way and was one of the first experiment that I did. So the history is not exactly linear. So did you manage to use C2Rust transpile? Okay. Did you try to use the -E option and see how the cargo tunnel and the generated lib.rs is being produced? So who is still fighting with it? Okay, so let me try to show you how it feels. So we have our libfoo. We call Mason build. And we want to transpile. I gave you the two options. So we look at the one that generates the cargo tunnel, and you see how it is. So we need to pass to C2Rust the compile commands.json. This is a sort of standard representation of a build plan. CMake can make it, Mason can make it. You can use a number of tools to generate the same thing from Make and from other build systems, but requires more effort. And you do this. In this case, I already did that. So let's remove everything first. And as you see, the process itself is fairly quick. And what we get is cargo tunnel out of the blue. As you can see, the only dependency that we have here is libc. And you can see that it's generating something that is a bit more creative. So it's not using the defaults. And if we look at the previous code, here is something that is nightly only. And this kind of special decorator is just telling the Rust compiler that this module is actually in a different place. So all of this is a fair amount of unneeded code, lots of boilerplate. Why is doing that? Because there is another tool in C2Rust that let you refactor the code using some kind of automation. Personally, I don't like it, since it feels more work than just doing that by hand. But it's good to know that it does exist. And then if we could go and see at the generated code, the whole thing is already a bit strange. So those are the C functions that are being used. And on my platform, that is Mac, we're starting to see some of the platform leaking. So this conversion is working on my machine. And if I want it to work on other platforms, I need to do changes. Since we have up to there code that we shouldn't care about. And from here, this is the auto-generated code. And as you can see, it's fairly ugly. But as you can see, Ismace is working. So Calloc is taking a SAST that is mapped to CU long. And since it's one, it's first mapped to int. And this kind of stuff looks fairly silly, but it's just how the compiler looks at things. So we are seeing what the C compiler thinks and how the Rust compiler could reproduce the same steps. And our compute function is having this. So you have this value that got promoted to double, and then multiplied by this value that is an integer promoted to double as well. The whole thing demoted to int. Same thing here. And because sin and cos are the word they are, this is what it's doing. And because it's a direct translation of C, you have this unneeded mutable modifier for those two variables that are not changed at all in this function, and then returns that. So what you can do once you have that is to just take the code, clean it up a little, and you get here. When I say clean it up a little, I mean that I didn't completely remove that, since the step here are first make so that it builds, possibly without warnings, and then you can start removing all the libc holes. So the memory allocation, we are in Rust, we don't need to do that. fprintf, we can use just println. This code is kept as is, just because in that case I was lazy. You saw before that you can convert that to use the standard the Rust standard library calls. So instead of sin, use .sin for F64. And that's it. So once we got there, we do this, and in this case, we don't have anymore all those dependencies. So right now, my dependency is libc. Once we remove everything, we don't have any more dependencies. And the test still passes. So that's this part. And if you manage to get to this point, we are already pretty much 80%, 90% in the root. What is missing now is to make sure that this crate is going to export back the same API. So let's go back to the slides if you don't have questions. So far, everything is clear, everything is fine. Nobody's lost, besides who's still waiting for C2RUST to compile. Since we have about 30 minutes on the very last part. Actually, just to check who is still alive, I'm going to wait for you to say that you are. So far, okay, so I managed to kill about half of you. Okay, let's move to the next step. So at this point, we have something that is built just using Rust. And depending on how we did that, it fed all the code. So now we have the last step. We have our proper crate, and we want to make sure that the C library makes so that it behaves like the C library is going to replace. So what we are going to expect from a proper C library, since I deal as distributing code in Gentoo, and there are lots of libraries that are completely improper. What I mean? Well, a proper C library, you have the bare minimum for a proper C library, that is one or more valid headers. What I mean with valid, with the proper guards, the way that they are not causing strange problem, they are not going to collide with system symbols. And all I've said happened a few times, even in larger projects. Maybe just because they are not aware that double underscore is reserved, and by sheer chance they managed to come up with a symbol that is the same as the one that one C library is implementing, or something like that. So having the header valid is not that a given. And just a static library. We can have shared library and static libraries. The bare minimum is having a correct static library. The ideal situation is having a pkg config file that is telling us where to find the headers, when to find the libraries, which are the link lines, possibly having the headers in their home directory, since that makes so that if you're using more than one header, your include directory is not going to be increasingly large and possibly colliding one with the other. And let's say you would like to have a shared library. Shared libraries and static libraries have different pros and cons, and you have different ways to make them. What I mean, a static library is just an archive. So it's just a glorified zip in ways that contains the object code, the .o that usually we find. And that's it. What's the problem with that? You need to provide the link line, because in many cases, your static library still depends on some kind of shared library. That could be, if you are on Linux, libpthread, if you're using threads. So you have to tell the linker when you're linking your static library that it has to keep pthread in the equation, or math functions that in many cases are part of libm. So there is quite a bit of information that you have to store somewhere in order to properly link the static library. For the shared libraries, you have different problems. Usually, depending on the platform, the information about the dependencies is embedded in the shared object itself. But at the same time, you need to feed in additional information such as the library version, or in certain cases, also the run path for the library. So where the dependency has to be looked at and where you have to expect the library to be. In this case, Mac is sort of requiring lots of information. Linux is sort of requiring some information. Windows has to be different. So you have to produce a completely different and separate library just with import symbols. So for Windows, you need to do even additional work. And how we are in this. For the libraries, those are the constraints. So the C-header proper, well, we can uncraft it. We know the API, we know what we want to expose, we can uncraft it. Or we can generate it. For having a C API in the Rust code, we need to remember that the struct that we want to export has to have the proper representation or have to be opaque. So wrapper C. We have to make sure that the functions are not mangled. So we have to remember to no mangle. And instance safe function is the way we are going to present our function, because if we are using pointers, bare pointers, the function itself is unsafe. And when we want to build static or dynamic libraries in Rust, we have those two options. cdlib for the shared library, the dynamic library, the static lib for just the static library. So what would be our ideal C API? the API that makes our life easier. We would like to add just the path structures, or as much as it makes sense, because then Rust can optimize the memory layout, and on the C side, nobody is going to care. We would like to have clear ends regarding mutability of arguments. So using the modifier const and restrict where it makes sense. That makes our life implementing the API much easier and makes so that the user life is going to be sort of easier. We have to document the thread safety, because in C you have no way to put in the code the information about it. And that means that we can be lazy and say, okay, if you want to use that from C, you have to put a mutex around it if you're using it from multiple threads. Or if the API and the code is made so that everything works as intended, even if you call it from different threads, you just document it so the user knows how to do that. Same thing for the memory ownership. Who owns the memory? Who frees the memory? You have to tell it, because there is no way to know in C. And usually all of this is already something that proper C library do, but not as often as you would like, and sometimes not completely. Sometimes the memory ownership discussion is lacking, so you have to look at the code. Sometimes thread safety consideration is completely omitted, so you have just to assume that all those functions has to be called from the same thread. So what we have to do? So start with public field had to be repo C, otherwise it's not safe to export. The function to be exported, no mangled, otherwise the symbol is not going to be the one that you are going to expect. Extern is telling the compiler to use the proper API. The function need to deal with their pointers so they are inherently safe. You have to provide constructor and destructors that are going to be called in C. Special mention for enums. C enums are ABI unsafe glorified integers. And with ABI unsafe, I mean that depending on a number of situations, the size of the enum could vary. So it's fairly good to avoid using enums as function arguments. And this is something that has to bite you a couple of times before you stop doing that. Usually because enums sort of look nice. But in C, if you're using an enum as an argument, you can pass it any kind of integer and the compiler doesn't tell you much. In Rust, you cannot do that. And in Rust, an enum is a specific type, and only the discriminant that you define do exist. If you try to cast a simple enum to int and back, if it's not fitting the correct discriminant, it's completely undefined behavior. So the compiler can kill your dog and empty your fridge. How does the code looks? So I'm showing you some examples. This is SLED, that is a tiny database engine that is fairly fast and fairly good. And this is how you provide a constructor and a destructor for a struct. This struct is created by using a new. You box it, and then you convert the box to a raw pointer. Box is just a way to tell the compiler that you want to heap allocate something. And well, think about fat pointers if you like C++. And once you want to drop it, you just take the pointer, you convert it back to box, and then you let it fade from the scope, or you explicitly drop it. So the life cycle in C has to start with create and then with free. If you don't code free, then you have a memory leak. Again, from SLED, an example of a function that is a bit more complex. In Rust, we have slice. In C, we don't. So depending on what you prefer, you can pass the pointer and the size of the slice as separate arguments, or you can come up with a structure that you're going to, well, sort of map the same concept as slice here. And again, what you do here is to call the method by doing the reference. This is unsafe because there is no way to know if this is going to be null or not. So if you pass a null db, this function is going to crash and nobody is going to save you. And the compiler cannot tell you that you are doing something wrong. And then again, you end up doing many times box new and then into row or arc new. So you have something that is heap allocated and is also reference counted using an atomic operation to increase the atomic counter. Another example, this is from the EBUR 128 again. So this structure is made so that you have a number of fields. All of them are private. So this function is opaque for as you care about. And when you want to destroy it, because you have this kind of additional indirection, you have to drop them in order so everything is cleaned up correctly. And this is the other pitfall that you have to care about. Something interesting, if you want to keep the pattern of invalidate the pointer so you don't have anything dangling, you have to use mut, and then you have just to use ptr null mut or ptr null to actually write a null in the pointer. So what you have to consider is that when you write the headers, the C headers have to be in sync with your code. So if you do that, writing them by hand, the process is error prone. And every time you update the code, you have to make sure that the header is in sync. And the only way to save you is to write more tests and do integration tests. And it is usually a good idea, doesn't matter what. And so if you can get away writing a single header, you can use cbindgen. That is pretty much the evil twin of bindgen. One is taking a header and writing the equivalent Rust API. Bindgen is working across your code in the crate and try to produce a header by mapping everything that is public and representable in C. So it is quite handy. It does work. It has a number of limitations. The first one and the most serious one is that it can produce just a single header from a single crate. So if you are in a situation in which you have multiple headers in the original library, you have to come up with some solution to avoid that. That is, either you split the crate, and then you have the problem of exposing the library, and that requires you to link together the two static libraries as a single one. Is an amount of work. Or if the headers are entangled in creative ways, you end up to have to do more work. This is again something that is going to be worked on sooner or later. Or if you feel that is interesting for you, contributions are welcome. So for the C headers, we can auto-generate them, but we have limitation. For the C libraries, Cargo does have some support, but it's just a crate type. So if you are building a static library, what is the link line? We don't know. Cargo C can tell you, but the way it's doing that is as annoying as it could. You can do worse just by not providing the information. But this is really doing the least amount of work, and is still quite annoying to extract. The shared library, on the other hand, is completely lacking all the information that you are going to expect. So no versioning information, no run path information, no companion implementation library for Windows. For that, we are really lacking. So what we can do for that? First part, you need to call Rust C, and you need to extract this information from the standard error. Really, you cannot do worse than that. This is something that is really annoying. And this is something that should be fixed sooner or later. For the shared library problem, Cargo lets you pass additional linker arguments, so you can provide the information, and Cargo is going to tap Rust to actually put the information in the library. What's the problem? Well, it's an external crate. I made it. Would be extra nice if all this logic stays inside Rust C. But again, you have the problem of separation of concern, and you need to figure out where to draw the line between this is a concern of the compiler and this is a concern of the build system. So anyway, this is not an excuse to not have Cargo deal with that. So what I did, well, I tried to hide completely all this problem and make a tool that tries to do everything so you don't have to think about it. So if you use cargo C, you end up with the correct static and dynamic library. You generate the header using cbindgen. So if you are in the situation in which you are fine with a single header, you are fine. And it prepares the AppWicket gconfig file. So all the information about linking and finding stuff is at the right place. Best of it, you install the whole thing the way you want. So Cargo C sort of sidetracks all the problems and most of the annoyance that you have if you were just to use Cargo directly. So now we have exactly 4 minutes to do the exercise, and probably we are not going to make it. But the idea of the exercise that could be your homework is to try to go back from the high-level API to a C API and try to build the static library, the dynamic library, look at them, look at the symbols that are actually present using enum, and that would be. And the final exercise is to just run cbindgen and look at its output, and this will show you how easy it is to generate back and header. Last sort of exercise would be to just use Cargo C and see how the code works. I put some references, and Noiseless is a full conversion of neural network to remove noise that is written in C. And this is the implementation that is written in Rust that is also providing the same API as the C implementation and has the perk of being faster than the C implementation. And since we have 4 minutes, I don't know if you want to rush and try to do any of those exercises, or you want just to see how things works. And probably we could just pick one example, and I can just run that for you, or you can try to run that at the same time. So this would be up to you. So show you, this is Noiseless. So you can just do cargo build. and we have the code. So here we have the rlib and a binary. So now we want to use Cargo C to build it. Now we add something more. So there is the header that is having the same name as the C1. And all of this is auto-generated. So Cargo C by default is going to put the version so you can use it. As you can see, some structures are just opaque, and then you have the API, and also you have some line documentation. So how different it is from the original one, since I have it. So something that you have here is that the public header in the C code is also used for building. So this part is just present because the building requires this information to do the right thing. And yeah, just some little differences. But the thing is the same. And the PKG config is made so that, again, all this information is auto-generated. As you can see here, since I'm on Mac, if I want to link the static library, I need to pass this link line. So if somebody that is using ArcNoise wants to use Noiseless, just has to change the PKG config name, and everything is going to work the same way. So I guess now I will spare you to do the exercises. I can show you the C API. Usually when you build your crate and your crate that sells bottom Rust and C, you can use this feature called C API and conditionally compile the C API itself if you put it in a separate module. This is one way. The other way is to keep the C API as a completely separate crate. It's up to you what you like. And the C API itself is going to use libc because ArcNoise is a bad library since it's using file, and this is one of the portability sin, since files are special depending if you are on Windows or Unix. So you have lots of non-portable code around files, because on Unix you have file descriptors, and on Windows you have file handles, and they are completely different. So to support that, you have to figure out if you are on Windows or Linux and try to do something about it. And this is fairly annoying. For the rest, again, you consume or use pointers. This API is really bad in some ways, but the trick is always the same. You box your structs, you convert to pointers, you move them around, and you convert it back. This is the same as dropping. You just say, okay, I don't care about the return point, and it just goes away. So once it fades from the scope, the drop is implemented, well, it's called if implemented. The discussion about slices is the same, and as I say, this API is fairly bad because you pass pointers, but the size of the slice is just implicit. You have this, and as you can see, Windows is not part of the equation. So if you want to support Windows, you have to conditionally build this version that is Unix-like, and then do the same thing for Windows to get a file handle from the file. And I think that's it for today. I'm open for questions. Or I managed to kill everybody now.
All right. Hi, Luca. I'll be helping you out with any questions we have. We have at least one person alive.
Good.
Thank you for being here, by the way. We're really happy to have you, even if this edition is virtual. Nonetheless, thank you for coming.
It was great last year, and it's still good even this year, even if it's remote.
Yeah, we haven't had too many issues today, luckily, with the platform.
It did work fine.
What's that? Sorry?
The platform did work fine.
Yes, for today. We're very thankful for that. Since we're not having any questions come in just yet, I just wanted to ask if you had anything you wanted to say about your participation in Rust Lab.
Well, being remote makes everything a bit more detached, so I cannot prod people to ask me a question or check what to do, what they are doing by looming on them. So probably it's not as nice as last year, since people tend to be introvert, and well, you have to force people to interact and ask. And the other part is that I'm not seeing the face of the people on the other side. So right. I don't know if they are completely lost or just they are quiet.
Definitely. We appreciate you checking in, making sure people were either staying with you or falling behind. It's very useful.
So beside that, well, I hope that you would enjoy that, even if, say, it feels more detached than it used to be. And well, say the platform was fine. You were great in organizing, and Well, I miss Flores.
It misses you too, I'm sure. Well, we're all very lucky to have great collaborators. We've all been working really well. So I guess since we don't have any questions coming in, hopefully everyone found that quite useful. So Luca, thanks again for you coming. Hopefully next time it will be in person instead of virtual. Let's cross our fingers for that.
Let's hope.
All right. All right. Well, I will let you go. Again, thanks so much, and hopefully you have a great rest of your day.
Thank you. You as well.
Thank you so much, Luca.
Okay.
All right, you guys. So that is it for day 4 of Rust Lab. So let's see. Tomorrow we have day 5, of course, which will include another workshop, this time by Alessandro Pezzato, called Create a Web App with You and Rocket. So hopefully we'll catch you all there. Enjoy the rest of your day. Oh, and I just wanted to remind everyone that if you liked this workshop, you can also rate it on the agenda page of the Rust Lab website. Oh, that's a mouthful. All right, everyone, this has been the conclusion. So take care and see you tomorrow, hopefully. Goodbye.